Assalamualaikum. My name is Dania Batrisha, ID 18002463. For lab report fluid dynamic, I will present on Bernoulli's theorem demonstration. For the introduction, energy exists in the form of pressure, velocity, and fluid elevation, with no energy exchange due to viscous dissipation, heat transfer, or shaft work. The relationship among these three forms of energy was first stated by Daniel Bernoulli, based upon the conservation of energy principle. Bernoulli's theorem related to a flow streamline is based on three assumptions: steady flow, incompressible fluid, and no fluid friction losses. The validity of Bernoulli's equation will be examined in this experiment. The objective is to investigate the validity of Bernoulli equation when it is applied to a steady flow of water through a tapered duct. The first step is place the apparatus on the hydraulics bench. Then position the outflow tube above the volumetric tank. Then level the apparatus base by adjustment of its speed and using spirit level. The third step, purge air from the pressure tapping points and manometers by connecting a small tube from the air valve to the volumetric tank. Allow flow through the manometers to purge all air from them. Slightly open the air bead screw. Retighten the screw back when the manometer levels have come to a convenient height. The maximum flow will be determined by having a maximum H1 and minimum H5 manometer readings. The fourth step, adjust the discharge valve to a high measurable flow rate. After the level is stabilized, measure the water flow rate using volumetric method. The sixth step, observe the pressure head for every 6 points by reading the manometer tube. Observe the total head at each point using hypodermic probe. The seventh step, ensure that the total pressure probe is retracted from the test section. Measure the flow rate by the time volume collection for at least a minute. Use a stopwatch to measure this time it takes to accumulate a known volume of fluid in the tank from the side glass. The last step, perform 3 sets of flow. This is the setup of the experiment. The Bernoulli test apparatus consists of a tapered duct venturi, manometers taped into the venturi, and a hypodermic probe that can be transversed along the center of the test section. A series of side hole pressure tappings are provided. From this figure, the dimensions of the test section, the tapping positions, and the test section diameters are shown. The test section incorporates 2 units, one at either end. A probe is provided. This is the raw data obtained from the experiment. From test section H1 to H6, the volume, the time, the static head, and the total head are measured. This is the results obtained. The test section, the distance into duct are shown in figure 2.2. The static head and the total head are measured in the raw data. As for the flow area, the flow rate, the velocity, the dynamic head, and the total head are calculated. There are 3 graphs. This is the graph of test 1. This is the graph of test 2. This is the graph of test 3. These are the formulas used. For Bernoulli's theorem, the first term is called static or pressure head, the second term is the velocity head, and the third term is the day term, which is considered 0 in horizontal type. For the discussion, from the result, as the diameter of the cross-section decreases, the velocity along the distribution tube increases. The smallest cross-section gave a big pressure difference and had the highest velocities. Other than that, as fluid flows through the venturi meter, the head is higher at the narrower tube. The narrower tube leads to low pressure and high velocities. For each trial, the volumetric flow rates are calculated. Each trial had different volumetric flow rates to control the outcome of the velocities, and the calculated volumetric flow rates were substituted into the continuity equation to determine the velocities. From the calculation, the highest velocities is caused by the highest volumetric flow rates. To calculate the velocities of every cross-section, Bernoulli's equation and the continuity equation are used. All of the measured Bernoulli's equation had the highest value compared to the continuity equation. With uniform density of water, continuity equation took account the area of cross-section, where the velocity decreases when area increases. Continuity equation is directly proportional to the area. Hence, the pressure will decrease when the speed increases. Both equations were suitable to be used to calculate the velocities. However, some parameters such as pressure difference and location are taken into consideration. For conclusion, as Bernoulli states that high velocity fluid flow results in low pressure, and based on the continuity equation, the velocity increases when the area decreases. The result proved both equations can be used to determine the velocity of fluid flow in manometer. Even when the values aren't exactly similar, the trend of increasing and decreasing at the converging and diverging portion is the same. As the velocity increases, the total head increases for both the convergent and divergent flow. The inconsistencies may be due to errors occurred in the experimental procedures. These are the potential errors that can be avoided. That is all from me. Thank you.